Are you able to hear me, Ribhu?
Yeah, I can hear you.
Hi, good morning.
Good morning. Oh, good evening to you guys.
Yeah. Okay, yeah, we can see that. Very good.
I don't know what. Can you see my mouse pointer? I don't know why. I
Yeah,
don't see it.
we could follow you. Yes, looks good. The voice is clear.
Yeah.
We'll just start in a minute or so.
That's fine. That's good. Thanks.
So welcome everybody to the last talk of the day, this evening session. It's going to be given by Ribhu Kaul from Penn State University. And he's going to talk about duality and domain wall dynamics in cobalt niobium oxide. Thanks, Ribhu. It's great to have you. And we look forward to listening about the recent developments taking place and understanding the system.
Okay, thank you so much. I'm just having a little bit of, here we go. Okay, so yeah, the problem is when I go to full screen, I can't see the mouse pointer, but maybe that doesn't matter. Well, well, thanks a lot, Yasir and all the organizers of this conference. So I'm going to tell you a little bit about this material cobalt niobate and about our work in it. And I recently moved to Penn State, and we're hiring both grad students and postdocs. And so if there are people who are interested, please contact me. I'd love to hear from you guys and talk about possibilities. So this work was done in collaboration with my grad student when I was at Kentucky, Nishita, who's now at Tata Institute, and I think she's also in the audience, and Peter Armitage, who's a experimentalist at Johns Hopkins. Okay, so I'm going to give, because this is a very short talk, I'm just going to give a very, very, very brief introduction. So, this transfossilizing chain is such a beautiful, simple model. It's just a model of one-dimensional quantum mechanics. And you all know the phase diagram at very low. So it has an external field and has exchange coupling. When the field is very small, the magnet polarizes in an easy access manner, either in the plus or minus z direction. And when the field is very large, it polarizes along the x direction, along the field direction. And this model is very profound. It has, lots of some of the most profound physics of the 20th century, surprisingly. The phenomena of spontaneous symmetry breaking, the idea of quantum critical phenomena, conformal field theory, duality, and these are just a few things. Actually, it has a lot of this is actually special. Some of it, that I guess, the idea of self-duality, at least to the one-dimensionalizing model. So a very important role in this talk is going to be played by domain wall excitations. So one of the very interesting features of this model is that when it orders, its excitations have a topological character. And this is not special to the transfossilizing chain. In fact, this is true about any one-dimensional easy axis magnet. So if you take the ferromagnet and ask what is the lowest energy excitation, it corresponds to this picture on the left, which is a domain wall in which there's just one unhappy bond. Now, the interesting thing is that to create this excitation, you have to change a macroscopic number of spins. And in an experiment, typically when you just flip one or two spins, you always create pairs of domain walls. Okay, so if you begin with no domain walls, you can only create an even parity number of domain walls. And it turns out all of this has some very profound implications for experiment. Okay, so very briefly, this is the material that I'm going to talk about, cobalt niobate. It has an orthorhombic unit cell. It's a Mott insulator, and it's magnetic because of cobalt ions. And the cobalt are in this 2+ state, where they have an odd number, it's 3d7, I believe, of electrons. And so they have a Kramers degenerate ground state. And this is what results in the magnetism, in the magnetic moment in the system. And so, in some very simplistic way, you can think there's a simple, small bar magnet on each cobalt atom. And, this cobalt 2+ electronic configuration has been emphasized by various authors. Liu and Khalilin, and there's another set of authors who I'll talk about later, who emphasize that this could have a J equal to 1/2 ground state, and spin orbit coupling could be strong even in a 3D 3D transition metal. So the crystal structure is such that in this material, the cobalt ions form chains in the C directions. Remember, it's an orthorhombic crystal. And if you look in the direction perpendicular to C, the AB plane, these chains form a triangular lattice. Now, I won't talk too much about the 3D structure, but the important thing is that the spacing between the cobalt atoms and the way they're bonded make it such that the exchange paths and exchange constants in the C direction are much stronger than AB. So this has been verified both ab initio and in many, many experiments over 30 or even 40 years. So now, some experimental things that have been known for a long time about this material is that it's an easy access magnet. So, of course, I discussed the cobalt electronic structure, but this is just known from experiments on the entire magnet. So it's an easy access magnet. The moments align ferromagnetic along chains. The moments lie in the AC plane. Okay, so all of these are very important. It turns out that there's some experimental details which may be not so important for the talk, but not all even when it's a ferromagnet, not all the chains align in the same direction. Okay, so there's this plus minus 31 degrees, which we can talk about later. But interestingly, even both those moments still lie in the AC plane. So if you apply a magnetic field transverse to the AC plane or in the B direction, basically, it's transverse to all the moments, even though all the moments are not parallel. Okay, this is an interesting feature which allows you to apply a transverse field to all the spins in the system. And in fact, if you make the transverse field 5.5 Tesla, the system becomes non-magnetic. Okay, so you have an easy access magnet. It's one-dimensional, very one-dimensional. Of course, it's actually three-dimensional. And the exchange coupling is weak enough that if you apply a 5.5 Tesla transverse field, you can make the system non-magnetic. So all of this sounds very much like the transverse field Ising chain, which I described early on as like a very profound model. It's very exciting, and this idea was really emphasized by Ribhu Kaul in a very beautiful paper in 2010. And so what he did was neutron scattering. And again, since this is a conference on frustrated magnetism, I don't have to show you what neutron scattering is. But this is the neutron scattering intensity for a momentum along the chain C direction and the energy. And what it shows at 5 Kelvin is that you have some very broad continua. And if you cool the magnet down to 40 millikelvin, this broad continua splits up into resonances, which are shown on the right. Again, I've shown the Brillouin zone over here on the corner. And you see that the Brillouin zone is also, I guess, I don't know what you call it, a cuboid maybe. And so the cut that I'm showing you over here is in the 0, 0 KZ direction. Okay, so KX and KY are 0, and KZ is the direction along the C axis along the chain. Okay, so there's a very simple physical picture that arises now. So remember, as we discussed earlier, in an experiment, you always create pairs of domain walls. And because you create a pair of domain walls, and if you look at zero momentum over here, okay, so unfortunately, or maybe not unfortunately, just the way the experimental data is taken, zero momentum is not at the center of the plot. Okay, it's on the right. It's where the bottom of this continue is. And so when you shine neutrons on this, or you shine light later, as I'm going to talk about, you always create pairs of domain walls. And because you create pairs of domain walls at zero momentum, they don't have a well-defined energy, right? You can have these, if you see this cartoon over here, you can have two domain walls which sum up to zero momentum at various energies. And this is why you have a continuum. But this changes when you go down to very low Kelvin. So when you go from 5 Kelvin to 40 millikelvin, the magnet orders, remember the magnet orders are 2.95 Kelvin. And then the neighboring chains create a self-consistent Weiss field. And now there's a very beautiful piece of physics is that if you think about these two domain walls, you can't, as you move them further away from each other, they experience a linear potential because the number of spins that are overturned against the Weiss field increase linearly as they separate. And so you have a bound state problem in a linear potential. This is a sort of classic problem that many of you may have remember you've solved in quantum mechanics when you solve for the WKB approximation and you linearize the potential. Okay, so the solution for the Schrodinger equation is well known. It's there's some airy functions. And so Koldea in some very nice work showed that there are resonances in the neutron scattering experiment. So it's these resonances that are shown on the right. This bright, unfortunately, my pointer, if it's working, I can't see it, so I don't know where it's pointing. But you have all these resonances on the right, and these resonances match up very well with the solutions of the bound state problem. Just solving linear Schrodinger equation. It's a very beautiful example of how, in a very complicated material, you see some very basic physics. And if you just saw this, I think it would be pretty good, but it gets even better. It turns out that when you increase the transverse field and you approach the critical point, you can't solve for individual bound states anymore because there are many domain walls, and you have to solve a many-body problem. And this was solved actually by Zamolchikov in 1989 in a very tour de force piece of work. And he showed that these first two resonances, so if you look up here, you have M1, M2, M3, M4, M5. And their work argues that basically these first two resonances, the ratio of them is the golden mean. In fact, they calculated the ratio of the first, I forget, 8 of them, but then the 6 higher ones are buried in the continuum. But the fact that you could, in an experiment, you could measure this golden mean, which is a non-trivial prediction of conformal field theory, was very, very beautiful. And so this work by Koldea, I think, is pretty amazing. Okay, so my collaborator, Peter Armitage, revisited all of this with a different experimental probe, which is terahertz light. So terahertz light is also in the same energy range in which some of these effects that we discussed are observed. And, again, because it's a short talk, I'm not going to go too much in the details of the talk, but I'm happy to tell you about this, where you send a pulse of light and then you can actually measure the electric waveform of the light. And that's shown at the bottom in picoseconds. And so when you Fourier transform this, you get peaks corresponding to exactly the resonances, which are exactly the same place as in the neutron scattering experiments. So this is a way of measuring bound states. The advantage of this experiment is it has very high resolution, and it's much cheaper to do this experiment than neutron scattering. So Peter was able to collect data of the evolution of these peaks for many magnetic fields. Okay, so in fact, almost continuously as a function of magnetic field. So remember when I showed you neutron scattering data, I had some at very low, at zero field, and then some at the critical field. And there may be other fields, but not many of them were published. On the other hand, in this case, you can measure this very with great accuracy, and you can measure its evolution in the transverse field. And right at the end of the talk, I'll tell you there's other cool things you can do with optics, which you can't do with neutron scattering, which are very exciting. And we're thinking about some of those things. Okay, so this is the experimental data. Okay, so there's an experiment taken at 3 Kelvin and 1.5 Kelvin. So again, 3 Kelvin is above the ordering temperature, 1.5 Kelvin is below the ordering temperature. And if you look on the right, so let's focus below the ordering temperature, that's when you have these discrete resonances, and those are those black or oscillating black and orange lines. And then you see that this evolves in some interesting way as a function of magnetic field. It's very nice. It has a lot of structure, but when Peter collected this data in 2015 or 16, he wasn't able to understand exactly what all this structure was. I mean, it's clearly beautiful, and there's some interesting explanation. And I was very lucky that he came and visited us in Kentucky, and we started to talk, and he had lots of interesting ideas about how to interpret this experiment, and that's when we started collaborating. So first of all, the interesting thing is that this experiment data doesn't look at all like the transverse field Ising model. Okay, so if you look at this data, the transverse field Ising model, what should it do, right? So if you apply no transverse field, the domain walls have no dynamics. So you just have a flat band of domain walls. Then as you increase the transverse field, of course, the domain walls get a dynamics that increases with the transverse field. And these split up into resonances. So I've shown you this actual data that Nishita took on the transverse field Ising model with DMRG. And then at some point, of course, the band becomes so dispersive that the bottom of the band crosses zero energy. And that's the condensation of, it's like post-condensation of domain walls. And that signals the transition to the disordered state. Okay, so in contrast to that, the experiment has all kinds of weird features. First of all, it has huge dispersion even without a magnetic field. In fact, the dispersion that it has without a magnetic field is basically the same order of magnitude as the gap itself. So whatever's creating it is not a small perturbation. It's sort of intrinsic to the physics of the cobalt niobate. And then when you apply a magnetic field, this doesn't happen at zero field, but when you apply a magnetic field, the resonance is split up in this very interesting way into what roughly looks like three features. You have a bottom feature, which also does some interesting things. Then you have an upper feature, and you have some middle dispersionless feature. So all of this was a mystery when we started thinking about it, and it was clear that this must have an interesting explanation. And that's what I'm going to tell you about today. Okay, so we'll get back to this experimental data in a little bit. But our inspiration was this work by Jakeli and Kaliulin, it's classic work in 2009, which I'm sure you've heard a lot about in this conference, about directional dependent interactions. Then there's follow-up work by Lee Kaliulin and Sano, Kato, and Motome. So the original proposal was to look for this kind of bond-dependent interactions. I'm not going to introduce this because I'm sure you've heard about this in iridium compounds. And then, as you all know, it became a big thing in ruthenium compounds. And then in this recent 2018 work, it was emphasized that even cobalt, which is, so we're moving from 5D to 4D to 3D, might have spin-orbit coupling that's strong enough that this could be an important effect. Okay, another interesting thing is that if you look carefully at the cobalt niobate crystal structure, remember it has these chains, but these chains are not linear. They actually turn out to be zigzag. And if you look at the zigzag chain, it's exactly a one-dimensional section of the ruthenium chloride crystal structure. Okay, so it consists of edge-sharing octahedra. Now, it turns out both in ruthenium chloride and cobalt niobate, the crystal structure is not perfect. In fact, in cobalt niobate, it's less perfect. It's quite distorted because it has lower symmetry than ruthenium chloride. And we'll discuss the effect of all of these things. Okay, so this was our inspiration. I would say it's an inspiration in the sense that, we don't literally take what they do and they try and derive some Kitaev model. And instead of doing that, we just ask ourselves, okay, if spin-orbit coupling is weak, we have to worry about the fact that the interactions may be bond dependent. And then, of course, in the Ising model, they're not. And they must be alternating because if you look at this crystal structure, and I guess here's a blow up of the crystal structure, if you translate instead of going from the cobalt atom to the next cobalt atom, but if you go to the next to nearest neighbor, so you shift yourself by two cobalt atoms, like I've shown in this red line over here, that's the fundamental translation of the crystal. So if you do that, of course, the exchanges must be periodic. But if you do it by one, it may not be periodic. So our idea was, okay, well, this material is an easy access magnet. So to make a very, very simple model, let's assume that nearest neighbor cobalt atoms interact with an Ising interaction. But even if you make this assumption, you cannot assume that the Ising axis is the same as you go from bond to bond. But of course, if you go from bond to next nearest neighbor bond, it must be the same. And so that's shown in the bottom over here. So you have two Ising axes in this material for a single chain. And they repeat in an alternating fashion. Okay, but so this is an interesting model, but it turns out that there's no symmetry in this crystal that forces these two Ising axes to be perpendicular. Okay, so if you thought about the Kitaev model and a section of the Kitaev model, then obviously these two Ising axes would be exactly perpendicular. But it turns out that in this material, there's no need for them to be exactly perpendicular. They can in fact be at any angle with respect to each other. Okay, so, but it turns out that, okay, so the angle between them is not fixed. It can be anything. It's not fixed by the symmetry of the crystal structure. But if you know where one axis points in the crystal, you can tell where the other axis points because there's a symmetry that exchanges the bonds. Okay, in fact, this symmetry that exchanges the bonds is the Ising symmetry, which gets broken in this material. And there are different ways to see it, but the simplest way to see it is that if you look in the space group PBCN, there is a C2 axis, 180-degree rotation through a cobalt site in the B direction. Okay, so it turns out that when you do this, you interchange the even and odd bonds. But now again, because you have to rotate the moment in, so when you do the rotation, you have to rotate the sites, but then you have to do an internal rotation of the moment. And because of this, it turns out that if you know one of the crystal Ising axis, the other one is fixed, and that's shown in this picture over here. So if I pick one to be in an arbitrary direction, then the other one is fixed because remember this pi rotation changes the even and odd bonds, but it also, so N1 and N2 are rotated by pi along the B axis. Okay, so that's an interesting fact. If you know one axis, which is not surprising because the crystal structure is so symmetric that the bonds are clearly related by some symmetry. And then, of course, there are all the other chains in the system, and they're also connected by some translations, inversions, other things. So once you fix one Ising axis, all the Ising axes in the crystal are fixed, including the angle between N1 and N2. But because you can let this first axis point anywhere, this angle between N1 and N2 is arbitrary. Okay, and it turns out that as you can convince yourself, if you just study the many-body problem, it only cares about the angle between the two. It doesn't really care about where it's oriented. If you're interested in the details of the experiment, it's actually important where it's oriented. So we call this model the twisted Kitaev model, and it is basically an Ising model which has alternating Ising axes which are not perpendicular to each other. Okay, but in fact, they're determined by some angle which I'll call theta. And the question is, what are the excitations and phase diagram as a function of theta? Okay, so this is a very simple many-body problem. You have this Ising chain. And again, physically, when you do this rotation about a cobalt site, you interchange the even and odd bonds. And now you could ask, okay, so what happens to this magnet? What is the ground state? So at least classically, the ground state is very simple. It turns out when this angle theta is less than 45 degrees. So of course, if it's 0 degrees, you get back the Ising model. And then the magnet polarizes in the Z direction, which is the direction in between N1 and N2. And in fact, when you let this angle theta go away from 0, it remains polarized in the Z direction until you cross 45 degrees. And when you cross 45 degrees, it'll polarize along the X direction. And at 45 degrees, the model is sick. Okay, so in fact, this was studied by, I just had a child a few months back, and ever since then, I can't remember anything. But I think this was Diptiman Sen and Shankar and other people who studied the classical Kitaev model and showed up the very beautiful paper about the degeneracies of that model. And in fact, they even showed, I think, in one dimension that this at 45 degrees, this model is very frustrating. It's sick, actually. It has like some extensive degeneracy. But it turns out we won't be interested very close to 45. But away from 45, it turns out that the magnet polarizes in this sort of, in the direction which makes a smaller angle between N1 and N2. So it'll be the Z direction in this picture. Okay, so let's take this model and let's work in this new axis. Since we know it polarizes in the Z direction, instead of working along the Ising axis where it's a little bit less clear what's going on, let's rewrite it in terms of the Z. The X direction is the B axis of the crystal, which is perpendicular to Z. And then I'm going to rewrite the Ising moments in this basis. And so you have an Ising interaction, tau Z, tau Z. Then you have this interesting tau X term. But the more interesting term is the next term. Okay, so this is a very interesting term which plays a very important role in our analysis. And it's a weird term that you wouldn't have thought you should write down or you could write down. So it's a tau x times tau z, and it has a -1 to the bond number, which appears over there. And again, because the symmetry of the crystal. So when you learn the Ising model in a simple thing, you learn that, oh, if you rotate around the x-axis, that's the Z2 symmetry by pi. That's the Z2 symmetry of the Ising model. Now, in the spin orbit, in this real material, it's not enough to just rotate the spin. You have to also rotate space at the same time. And because when you do that, what happens is even an odd bonds change. So this -1 picks up an extra minus sign. And then when you rotate by pi along the x-axis, tau z also changes sign. And those two signs cancel. And so this term is allowed by symmetry. In fact, this was pointed out in a very nice paper that appeared a few months before us by Fava, Koldea, and Parameswaran. And in fact, for cobalt niobate, and they have a very nice analysis of the neutron scattering data. Okay, so this is a simple model that we have. It has this, K is just the energy scale, but really has one parameter, theta, which controls the physics. And in fact, this, as far as we can tell by DMRG, the quantum ground state is very similar to the classical ground state. So it polarizes until you reach 45 degrees, and then it gets very hard to simulate because of all this sick behavior. So in some sense, it's a frustrated magnet because the Ising axis, alternating chains, alternating bonds are telling the spin to do something different. And it's choosing this Z direction polarization as a sort of compromise between these two conflicting messages it gets. Okay, and so now remember the external magnetic field, which was perpendicular to the AC plane, is now along the x-axis. So this is the experimental direction of the magnetic field. And finally, we're to put a magnetic field along the Z direction. Okay, the interesting point is actually this field, which is generated by the neighbors, doesn't have to be by symmetry along the Z direction. It cannot be in the X direction, but it can be it can have a component Z or Y. But for simplicity, everyone just takes the Z direction. And we can discuss that later if people are still interested. Okay, so this term again is very important, pointed out by these guys first. Okay, what's happening? There we go. Okay, so let's analyze this term, and I think I still have a little while. So let me. It's actually very fun. So let's assume that let's begin by thinking in terms of domain walls. So we'll assume tau z interaction is big. And as we discussed earlier, if you just assume tau z interaction is big, then the lowest excitation is just a domain wall where you flip a half of the system and you have like a point like excitation. So the question now is that if I study this domain wall basis, this is a highly degenerate basis because I can put the domain wall anywhere I like along the chain. And in this space of degenerate domain wall states, I want to study what this term does, right? Because remember, the Ising model by itself has no domain wall dynamics, right? Domain walls are stationary. And this term clearly, because of tau x's, it starts flipping the spins and the domain walls can move. But it does it in some interesting way with this -1 and tau z. I mean, the normal way you study domain wall dynamics is you just apply external transverse field, which is just tau x. Right? And that just hops the domain walls. This is what you learn in basic many body physics. But now you have a tau z, you have -1, so the domain wall hopping is rich. And in fact, if you write this down on the right side, you see it's -1 to the I, tau z, I plus 1, minus tau z, I minus 1, tau x. So if you take this term and study it in perturbation theory, it turns out, first of all, notice that it'll only act on the domain wall. So if you consider some domain wall configuration, tau z I plus 1 is always equal to tau z I minus 1, unless you're exactly at the domain wall, right? Because then tau z and tau z won't be equal because the spin flips. And then what tau x does is it can cause the domain wall to hop, right? This is exactly the transverse field. But now the interesting thing is because it's -1 to the I, if the domain wall hops to the right, it hops with an amplitude of +1, and if it hops to the left, it hops with an amplitude of -1. Okay, this is very, very interesting. And so what we learn is that domain walls, if you think of the dual lattice, the domain walls, when the domain wall hops on even bonds, it hops with a positive amplitude. In an odd bond, it hops with a negative amplitude. It's very interesting. But in this pure model, the amplitudes, the magnitude of the amplitudes are equal, even though the sign changes from even to odd bonds. Okay, and on the other hand, if you just apply a simple transverse field like you would do in the Ising model, then the domain walls hop always with a plus amplitude on all bonds. Okay, so this is interesting and contrasting. And so obviously, if you have both this weird exchange and an external magnetic field, then you'll get a sum of minuses and pluses. And then what you'll have is you'll have the odd bonds have a stronger strength of hopping, and the even bonds have a weaker strength. And in fact, this is, when you learn about polyacetylene in the Schrieffer-Heger model, this is exactly what happens, right? When you have double bonds and single bonds between carbon atoms, you have strong and weak hopping. And so this hopping model, now we're talking actually not of hopping of electrons, we're talking about hopping of domain walls. It has a hopping very similar to the Schrieffer-Heger model. Okay, so this is the interesting domain wall dynamics that this term introduces. And of course, this term is fixed by chemistry, but then you can apply an external magnetic field, which you can tune yourselves, or the experimentalists can tune. And so what you have in the experiment is you have a combination of both. So now the interesting thing is, remember when you just have HX, we discussed long ago that the domain walls have no dynamics at 0 HX, and then as you increase HX, the domain, the band becomes more and more dispersive. It just sets the scale of the dispersion. But now the interesting thing is that because of spin-orbit coupling, we have this first term, and now we're adding HX to this. And what is the domain wall band structure? So first of all, because the hopping has a periodicity of 2, like you learn in, again, basic solid-state physics, you actually get 2 bands, right? Because you have to take twice the unit cell, you have 2 guys in a unit cell. So on the red over here, I've shown you these just line drawings, these actual line drawings of this calculation of the band structure. And this is, again, very much like the Schrieffer-Heger model. And you see some interesting things happen as you increase the transverse field. So first, when you have no transverse field, you have very dispersive bands, and they cross each other. Because remember, when you have no transverse field, even though you have even odd hoppings, you can do a gauge transformation and make them all even. Right? This is a famous thing. In one dimension, you can change the sign of all the each of the hoppings arbitrarily. Now, when you apply the transverse field, this changes now because you have odd and you have strong and weak bonds, right? Because you're adding a uniform thing to an oscillating thing, and so you get strong and weak. And that splits this, band structure into 2 bands. Then the bottom band gets flat at some value of HX. And if you increase HX beyond that, then it becomes dispersive in the opposite direction. And if you increase HX more, eventually the lower band, its minimum will go and hit 0, which is exactly Bose condensation, and you have Bose condensation of domain walls, and that's the Ising transition, right? We discussed this in the context. So at low fields, there's interesting things, and then when you go to very, very high fields, it turns out that you get back the Ising model, at least in this universal sense, right? The Ising model doesn't have the high energy bands, but then as far as critical phenomena is concerned, it doesn't matter. So now, when you do an experiment and you probe these domain walls, and I always show the experiment as a little hammer where you tap the system, because experiment is local, right? So because it's local, it creates pairs of domain walls. It cannot create single domain walls. So now I can take this dispersion E1 of a single domain wall, and I can ask, what is the energy of a pair of domain walls? And they have to have 0 momentum, because again, remember when you probe the system with light, the wavelength of light is much larger than the lattice spacing. It's 1,000 times larger. So as far as momentum is concerned, the light has no moment. It can't change the momentum of the system. So the system begins in 0 momentum ground state, the light shines on it and stays at 0 momentum. So now we're interested in the energy of a pair of domain walls which have total 0 momentum. And so I just take this E1 picture on top, and as it changes in transverse field, now I have to put 2 domain walls in this band structure. So I can put both them in the lower band. That's shown in the bottom. Unfortunately, I don't have a pointer here. And in between, I can put one in the lower band, one in the upper band. And then there's a third branch of these excitations where I put both the domain walls in the higher band. Okay. Now, for each of these guys, I can plot the set of energies in which you can create 0 momentum pairs of domain walls. And I can study this as a function of transverse field, and you get this interesting picture which is shown at the bottom, right? So you have three features, roughly speaking. There's this red feature, which is, almost non-dispersive. There's this lower feature that has this interesting, contraction, the green area where the domain wall has like no dispersion in the middle. That's because the domain wall becomes flat at some transverse field, like we see in the band structure. And then finally, as the transverse field gets larger and larger, this domain wall, the bottom green branch gets wider and wider. At some point, it hits 0, and that's when the Ising model has its transition. And so if you look at it now, this picture over here is just a cartoon that I've drawn without doing any serious calculation. It looks a lot like the experiment, right? If you look at the experiment, remember it has these three features, it has this thing. And so this green, red, and blue thing looks a lot like the experiment over here. So this was a hardening. And so when Peter and Nishita and I discovered this, we were very excited. And then we said, okay, well, but really this is just some perturbation theory, and we really want to compute the amplitude of all these processes, which is very complicated. So it's a many-body problem. And so we decided to study it with the DMRG. And so basically the idea is you take this Hamiltonian, you calculate the ground state, then you time evolve it, and then you act in linear response, in both new. So really, with light, you're studying a dissipative process, but by the fluctuation dissipation theorem, you can compute the response to light by just computing the dynamic structure factor that you study in neutron scattering. So it's basically a two-point correlation function in space and time when you Fourier transform it. Okay, so this is some very nice data that Nishita showed, calculated. Basically, the idea is this was an idea due to Steve White, and as a way of analyzing this, calculating these structure factors that he pioneered. And so at the bottom is t equals 0, where you have a chain, and then at the origin of the chain is your first SX0 operator, and that creates disturbances of pairs of domain walls that disperse out with some velocity as a function of time. And then you can take this data and Fourier transform it. You can Fourier transform in space and in time, and then you get momentum frequency graphs. And so we're interested, of course, in zero momentum. So we forget about the dispersion. We just focus at k equals 0, and then we study as a function of omega, and you get these nice resonances. And these resonances are exactly these two domain wall bound states that we were talking about in the experiment. Okay, so then we can study this as a function of transverse field, and this is the final picture that I wanted to show you here. So on the left is the experiment, and on the right is the experiment, and on the left, I'm sorry, it's early in the morning. Sorry, the ones on top are the experiment, and the ones below are the theory. Okay, so let me just walk you through this and explain to you how these plots were made. So we had to fit the angle, and we had to fit the overall scale on the y-axis, which is overall energy scale, and then we had to fix the g factor, but that's all we had to do. Actually, sorry, you have to also fit the longitudinal field, which is, so that's all you have to do for the left. But if you want the right plot, you have to turn on a longitudinal field, and you decide how big that is, but that's quite easy to do. And so let's look at the data. So first of all, over here, what happens, this is the upper plot is the terahertz experiment above the ordering temperature. And the below is the theory of the Ising chain without a longitudinal field. So remember, we said that what the experiment does at low temperatures when it orders is it creates a longitudinal field. So if you want to go to higher temperatures, we just study the same system. So we're doing zero temperature DMRG, but we're studying it without a longitudinal field. And then, the DMRG plot you get looks very much like the perturbation plot I showed you earlier, where you have these three domain wall sections. You have, I mean, of course, they don't look as simplistic as perturbation theory because the system is, at a pretty large angle. So it's not that close to perturbation theory. And, you see all these nice features that you expect in the experiment. And you also see this very dark line over here, which is a bound state outside the continuum. And we can talk about that. Now, when you apply the H0, then all the continua go away and you just get bound states. So all these continua, which are shown on the right, split up in exactly the same way as an experiment. And, you can identify, again, three different regions. So remember, I showed you can identify three different regions, and it wasn't clear what the interpretation of that was. And now we have a very nice interpretation of all of that in terms of spin-orbit coupling, domain walls, doubling of the unit cell. And you have these three regions, and they look very much like the experiment, right? So maybe in the interest of time, I shouldn't. So I have a few more slides, and maybe I'm running out of time, so I should be quick. But there's one more. So this is, we're very happy with this interpretation. But now the question is, what happens at large transverse field when the magnet disorders? And the transition happens through domain wall condensation. And this is beautiful result about the transverse field Ising model, which is called the Kramers-Wannier duality. And I mean, I'm sure I'll assume that you'll know what it is. And the idea is that if you take the original Ising model, it turns out you can rewrite the Ising model in terms of some new variables, which are related in some very non-local way to the original variables. But in these new variables, you actually get back the same Ising model. And so there's a sigma representation and a tau representation. And there's a very nice physical interpretation. Sigma, of course, is just the operator that creates spin, like we know. You write your Ising model in terms of spins. It turns out tau is an operator that creates domain walls. Okay, so this is a very beautiful thing. And basically it shows that, if you think of the Ising model at coupling J and H perpendicular in terms of spins, that's the same as the Ising model as in terms of H perpendicular and J in terms of domain walls. Okay, if you do this transformation twice, you come back to the original model. So that's why it's called a duality. But it relates points in the phase diagram which are symmetric across the critical point. And so it says basically that if you want to create, at a certain distance away from the critical point on the left, if you want to create a domain wall excitation in the ordered state, that's going to cost exactly the same energy as creating a spin flip excitation when you're in the same point on the right of the critical point. This is a very beautiful, remarkable feature of the Ising model. Now, the interesting thing is that we don't have an Ising model, either in experiment or in our theory. But as you reach the critical point, one expects that everything is universal. And so any universal feature that you calculate in the Ising model must be true about any model in the same universality class. And I said that our model also, the transition proceeds to domain wall condensation, so it's in the same universality class. So because the domain wall energy is exactly equal to spin flip energy, but there's one important detail. Now, because the experiment always creates pairs of domain walls, if I actually look in an experiment and I try to probe it, I'll find that the energy of the domain wall is exactly, the domain wall excitations come at twice the energy of a spin flip quasi-particle. So I always create pairs of domain walls. And in fact, this, you can argue, is a universal amplitude ratio. Okay, so this, if I study the ratio of the gaps, this is something in critical phenomena, which is called an amplitude ratio. It's universal. And so I can compute it simply using an Ising model, the Kramers-Wannier duality, but it must be true even for any one-dimensional easy axis magnet close to its critical point. So here's experimental data again, where we try to interpret the experiment in this way. So this was taken on a different experiment. And unfortunately, this is in Estonia, and the experimentalists here decided to plot the data slightly differently, and I couldn't convince either Peter or anybody else to flip the plot. So it's rotated by, it's shown in a different way, but it's the same data on a different experiment that can go to larger transverse field, but has lower resolution. Okay, so there's some experimental details I don't want to go into. The point is that, again, here you can see, this waterfall plot is higher and higher magnetic fields. And at low magnetic fields, you see that, so the low magnetic fields are right at the bottom. You see some interesting feature. Then as you cross, a few Tesla, you start seeing this domain wall condensation. And then as you increase the field, you can see a spin flip excitation increasing. And so if you extract the peaks, you get the picture on the right, which is something that I think all of us theorists can understand, and some experimentalists too. So you have these red things which show domain wall and spin flip quasi-particles. And again, if you look at it, it looks like a straight line, which is what you expect close to critical point, because z times nu is 1 in the one-dimensional Ising model. And if you calculate the ratio of this slope, it turns out to be 1.9 in the experiment. Okay, very close to 2. So this is very nice realization of this Kramers one. I mean, it's very beautiful because this 2 has a very simple physical interpretation. It would be 1 if you could create single domain walls. Then you'd be seeing Kramers-Wannier duality. And now it's exactly 2 because you create pairs of domain walls. Okay, so I think with that, I'm going to finish and just say that, there's this rich physics at low fields. So if you look at the experiment up to about 2 Tesla, there's all this interesting features of domain walls and their band structure and how they can be controlled by an external magnetic field. And then at high field, the system, shows this beautiful Kramers-Wannier duality, which has been known for 60, 70, 80 years, I guess now, maybe even 100, 80 years, I think it was sometime, a long time. And I think this is the first time, as far as I know, that it's been actually been able to observe an experiment, even though, of course, everyone expected it to take place. And so some, interesting takeaways is that bond-dependent interactions are very strong in cobalt. There's no other interpretation I think you can give for this experiment. You have to have the fact that interactions are bond dependent. There's a doubling of unit cell, which comes because of directionality of the bonds. And then there's some interesting future things we're working on is that, there's all this rich domain wall structure and their dynamics. And it turns out that with optics, you can do something we can't do in neutron scattering, is you can study nonlinear responses. And so there's a lot to study in this material still, even though we understand lots of it, the linear response pretty well. Okay, thank you so much. And I'm sorry if I went a little bit over.
Yeah, let's thank Ribhu for a wonderful talk. Really exciting. So we can now entertain some questions or comments.
May I start?
Yeah, please, Frederic, yeah, please.
Yeah, okay. Hi, Ribhu. Very nice talk indeed. And I have a question about the experiments. This is just on this slide, the top right panel. In experiments, there are some features at lower frequency, below those that you can explain. Are these artifacts or are these real features due to maybe more domain? Do you understand what it is?
Yeah, so I think you're talking about these. So
exactly,
if I get out of full screen mode, I get my pointer back. You're talking about these features over here.
Yes.
That is a great question. And I asked Peter that. And his understanding of what he told me is that it's a noise. Now, if you look at, so there are two experiments. The Peter's experiment is done with so-called time domain terahertz experiment, which is, where you send a pulse, you actually measure the shape of the electric field and Fourier transform. Now, when you measure the shape of the electric field, it is quite noisy. I mean, there's a lot of noise, and there's a lot of signal processing they have to do to even get data that looks this nice. So, I mean, I guess I don't know any other interpretation of that. There are those features, and we've thought about them. We don't have any interpretation for it ourselves, and so we've gone with what the experimentalists tell us is that it's probably noise. But it's interesting to think about.
Okay,
in fact, there's a lot of noise even in this. If you look here down here in the Fourier transform data, which is again, we expect this to be noise, but
in the other experiment, if you can show the slide, it's a very structured noise somehow, because there are really levels there. It's amazing.
Yeah.
It's, okay.
Yeah. No,
I was wondering whether you had an explanation for that, or it can of course be an experimental artifact. That's key. Okay. Very interesting.
It's very interesting. I guess. Okay, I mean, I think one thing that I would also say is that there's no evidence that this happens in neutron scattering, that there's anything down here. But again, it is faint, and you could argue that maybe in neutron scattering, the resolution is not good enough to see it. And maybe they didn't look at such low energy. So it could be something interesting, but I don't, I think our current take on it would be that it's noise.
Okay, thank you.
Thank you. That's a great question.
Thank you, Frederic. Any further questions online or offline? Any comments or thoughts? If not, then let's thank Ribhu for a wonderful talk. And with that, we close today's sessions. Yeah, thank you, Ribhu. Thanks a lot. Talks. It's time to take some rest now and enjoy the dinner in about an hour's time. We'll start at 7 p.m. at the cafeteria. And we meet again tomorrow morning at 9:40 a.m. For a tutorial by Deg Pert, which will be held here in person on NMR and techniques to probe frustrated magnets. So see you all later in the evening and tomorrow.
Okay, thanks, Yasir.
Yeah, thanks, Ribhu. Hope to see you soon sometime.